Okay, so welcome to this video. In this video, what we're going to talk about is the voltage-gated sodium channels. Okay, so the topic for this video is voltage-gated sodium channels. So, we're going to start off with a discussion of the action potential to give the motivation for studying the voltage-gated sodium channels. After all, the point of studying the voltage-gated sodium channels is because of their importance within the action potential. Okay, right. Then what we'll do is we'll have an in-detail study of their structure. Then what we'll do is we'll discuss their opening properties and what happens during inactivation. And then finally what we'll do is discuss some open channel blockers such as tetrodotoxin and saxitoxin. Okay, right. So the first thing to say is that voltage-gated sodium channels are often abbreviated to VG for voltage-gated, and then you can either put an S here for sodium, or you can put an N which also stands for sodium. Okay, but you're using the N because the periodic table symbol for sodium is Na. Okay, I prefer VGNCs to VGSCs. Okay, and then the C is just for channels. So people will often abbreviate voltage-gated sodium channels just to VGNCs, but you might see some people putting an S there for sodium. It doesn't really matter. Okay, right. So, let's start off then with the motivation for studying voltage-gated sodium channels in detail, which is to understand the action potential. Okay, right. So, in order to discuss the action potential, what we firstly need to discuss is the concept of electrical potential difference across the cell membrane. Okay, so let's start off with that. So basically, electrical potential is this concept from physics, okay? It's a mathematical model to help us understand reality, okay? And this is the mathematical model. To every point in three-dimensional space, you are going to ascribe a real number, okay? So to every little point in space, you give it a real number. Now this number can be positive, it can be zero, it can be negative. It can be an integer, it can be irrational, it can be an irrational. It can be any real number. Okay, right. So, in principle then, I can have a little man here with a special device that will measure electrical potential. Okay, and this little man can go to any point in three-dimensional space. So I'll try and draw a three-dimensional pair of axes here. Okay, he can go to any point in three-dimensional space and he can measure what the electrical potential at that point is, basically. Okay, right. Now, basically, if we take a cell now, so this is some cell, okay, so back to biology. Here we have a cell. Basically, all the points within the cell, so all of the cytoplasmic points here, those will all be in electrical equilibrium with one another. And therefore, to a decent enough approximation, they all have the same electrical potential. Okay, so the electrical potential of all of these points within the cell will be the same. Okay, now that means that this little man with his machine can go into the cytoplasm of the cell and he can wander around, and the number that he gets on his screen will be exactly the same everywhere. We will call that number the electrical potential within the cell. So we'll have big E for electrical potential, and then we'll subscript it I for intracellularly. Okay, so this is the intracellular electrical potential. Similarly, in the extracellular fluid, all of those points will be in electrical equilibrium with one another, and therefore all of those points will have the same electrical potential. So if the little man is wandering around in the extracellular fluid shaded here in pink, then the electrical potential of all of those points is the same, so his number on his screen will be the same. Okay, and we'll call that the electrical potential extracellularly. Now, to transfer that onto this diagram here, this is supposed to represent the phospholipid bilayer of the cell membrane. Okay, and this is the extracellular compartment, this is the intracellular compartment. So we have some electrical potential of the extracellular compartment, and then we also have an electrical potential of the intracellular compartment. Okay, and these two numbers are not necessarily the same thing. In fact, in most cells, they are not the same thing. Okay? Therefore, we have then the concept of an electrical potential difference, okay, a difference in electrical potential across the cell membrane. Now, an electrical potential difference is also called a voltage, okay, and I should just say that the number, going back to electrical potential now, remember we were ascribing a number to every point in space. That number has a unit, okay, and the units of electrical potential are volts, okay, so every point in three-dimensional space has this number ascribed to it, and the units are volts, okay, so that's just the units of electrical potential. Now, voltage is another name for electrical potential difference, okay, and strictly speaking, when people say the voltage across a cell membrane or the electrical potential difference across a cell membrane, what they mean is the electrical potential difference from extracellular to intracellular. Really, they should orient it. However, people often drop the from extracellular to intracellular because they assume that you understand this already, okay? So people, when they're talking about this, will often just say the electrical potential difference across the cell membrane, or the voltage across the cell membrane, or the resting membrane potential, okay? All of these things, strictly speaking, should be called the electrical potential difference from extracellular to intracellular, but people assume that you understand the direction in which we're going. Now, what does this literally mean then? It means if you had a little man standing in the extracellular fluid, okay, so he starts off in the extracellular fluid, he's got this machine, it's measuring the electrical potential, so it's showing him currently this number on his screen, the electrical potential of the extracellular compartment. Then he moves across the cell membrane into the intracellular compartment, and the number on his screen updates, and it updates to this new number, the electrical potential intracellularly. The electrical potential difference from extracellular to intracellular means how much would the number on his screen change if he moved from extracellular to intracellular. Okay, so we can now write this in terms of the electrical potential intracellularly and the electrical potential extracellularly. Okay? So, the change in electrical potential difference across the cell membrane from extracellular to intracellular means the new electrical potential, which is the intracellular electrical potential, so this is the one that he'll have on the screen of his machine at the end, okay, minus the old electrical potential, which is the electrical potential extracellularly, which is this number that he had on his screen originally. Okay, so that is what is meant by the electrical potential difference from extracellular to intracellular. Okay, right. So, this is usually kept at around negative 65 millivolts. Okay, so the first thing to discuss is that the units of electrical potential difference are the same as the units of electrical potential. Okay, this is millivolts, but that just means 1,000th of a volt. And that makes sense because all we're asking is a difference between two electrical potential values. And of course, that will be measured in the same units as the original values. Okay, so voltages are also measured in volts. Right, so what does this actually mean to say that the electrical potential difference across the cell membrane from extracellular to intracellular is negative 65 millivolts? What it means that the intracellular electrical potential is lower than the extracellular electrical potential, and it's lower by 65 millivolts. Okay, so that's what this literally means. Right, okay, so let's now discuss the action potential. So the action potential basically is going to be a maneuver of the electrical potential difference across the cell membrane at a little portion of membrane basically within a cell. Okay, now, in order to fire an action potential, you need to have voltage-gated sodium channels and voltage-gated potassium channels within your cell membrane. If you don't have those, you can't generate an action potential. Okay, so that's the difference between excitable cells, such as neurons, and muscle cells, such as skeletal muscle and cardiac muscle cells, and then a non-excitable cell, which can't fire action potentials. Okay, right. So, the initial thing that causes an action potential then is that you're going to get some initial depolarization in the electrical potential difference across the cell membrane, which will activate a voltage-gated sodium channel. But before we start the discussion of the action potential, let me firstly just put in the voltage-gated sodium channels and the voltage-gated potassium channels on our diagram. Okay, so let's say this will represent our voltage-gated sodium channels. So at the moment this is a single voltage-gated sodium channel, coloured in orange, and at the moment we've got a very simple diagram of this. We will go a lot more in detail than this, but at the moment we'll have a very simple diagram here. So this is a voltage-gated sodium channel, and we'll also put in our voltage-gated potassium channel here. Okay, now voltage-gated potassium channels are often abbreviated to VGKCs for short, so K is the periodic table symbol for potassium. Now, we won't be going into any more detail than this for voltage-gated potassium channels. They will remain being represented like so. Okay, right. Now, this picture is slightly badly drawn because initially they will both be closed. So imagine that they're closed at the moment. Okay, they're going to be activated by depolarization of the electrical potential difference, but we haven't done that yet. I've drawn them open so that when we actually do open them, they're ready and waiting, okay? But at the moment they should be closed. Right, so whilst we're at resting membrane potential, this negative 65 millivolts, these two voltage-gated sodium channels and voltage-gated potassium channels will be closed. And again, understand that although I've only drawn one of these and one of these, there will be a huge number of them in this little patch of membrane. Okay, so what's going to drive the beginning of an action potential is you're going to get something which is going to cause an initial depolarization in the electrical potential difference across the cell membrane, and that initial depolarization is then going to activate these two types of channel. Okay, so often what will cause this initial depolarization is some sort of channel opening, a sodium channel opening generally, and this might be some sort of ligand-gated ion channel, or it might be some sort of other receptor for something other than a ligand. For instance, maybe a thermal receptor that opens in response to too hot or too cold stimuli, okay, or potentially a mechanical receptor which will open in response to mechanical stimulation. Okay, the point is this is some sort of channel that has opened, and generally this channel will conduct sodium ions and allow sodium ions into the cell. Okay, but it could be other ions such as calcium ions, or it could be allowing chloride anions out of the cell or something along those lines. Right, okay, so, but generally it's sodium ions. So, we've opened this channel, okay, in response to some sort of stimulus, and this is now going to allow sodium ions to move into the cell. Now, why will sodium ions move into the cell through this channel when we open it? Well, for that, we need to discuss the different concentrations of sodium ions outside the cell and inside the cell. Okay, so the concentration of sodium ions in the extracellular fluid is around 145 millimolar, whilst the concentration of sodium ions in the intracellular fluid is around 12 millimolar. So the concentration gradient is 12-fold, favouring the movement of sodium ions into the cell, simply because a sodium ion is 12 times more likely to hit this ion channel from the outside and go inwards than a sodium ion is to hit from the inside and go outwards. Okay, in addition, you have to factor in the initial electrical potential difference across the cell membrane, which is negative 65 millivolts. Okay, that means that the electrical potential intracellularly is 65 millivolts lower than the electrical potential extracellularly. Sodium ions are a positively charged ion. They prefer to be where the electrical potential is lower. Okay, all positively charged ions want to be where the electrical potential is lower, which is currently the intracellular compartment. So not only is the concentration gradient saying go in, but the electrical gradient is also saying go in. So as soon as you open a sodium channel, this will generate a current of sodium ions into the cell. So don't fear the word current. All current means is a movement of charged particles. Sodium ions are charged particles, so we have got a movement of charged sodium ions into the cell. So that's a sodium current, basically. Okay, and this sodium current is going to cause the depolarization of the electrical potential difference across the cell membrane, and this is what's going to start off the action potential. So the only reason for discussing this is so that we can discuss how the action potential actually begins, so that we're not just sort of like leaving that bit out. I would like to, have a complete discussion of how this happens. So, people usually draw a graph like this when discussing the action potential. Okay, so what they do is they plot the voltage across the cell membrane from extracellular to intracellular on the y-axis, and then they plot time on the x-axis. Now initially, our cell was quite happily sitting at this electrical potential difference across its cell membrane of negative 65 millivolts down there. Now, when you move this sodium ions, these sodium ions, into the intracellular compartment, you are going to change the electrical potential difference. So when you deliver the stimulus, okay, at this time here, that's going to be where this current starts coming in. So this is the point where the stimulus comes in, and that's going to kickstart the entire process, because this sodium current is going to change the electrical potential difference across the cell membrane. Now, why is that? Well, basically, when you move positive charge into an area, such as what we're doing here, what you're going to do is raise the electrical potential of that area. So you're going to raise the electrical potential intracellularly. In addition, where did you get this sodium which you're moving into the cell from? It came from the extracellular compartment. So you are grabbing sodium ions from the extracellular compartment and chucking them into the intracellular compartment. Chucking them into the intracellular compartment raises the electrical potential of the intracellular compartment, but removing them from the extracellular compartment also reduces the electrical potential of the extracellular compartment. So this number goes down, this number goes up. So what effect is that going to have on the electrical potential difference across the cell membrane? Well, initially the electrical potential difference was that the intracellular electrical potential was 65 millivolts lower than the extracellular electrical potential. But now this number is coming up and this number is coming down. So the amount that you're going to have to go down when you move from extracellular to intracellular is going to become less. So this number is going to become less negative, basically. If you want to see that in terms of this equation here, this number is going up here, and this number is going down, so this number is becoming bigger, and the number you're subtracting off is becoming smaller, so of course it's going to become less negative. Now the fancy word for the electrical potential difference across the cell membrane from extracellular to intracellular becoming less negative is to say that the electrical potential difference across the cell membrane is undergoing depolarization. Okay, so it's becoming depolarized. Now, if we plot this on the graph, what this is going to look like is a sudden upswing, basically, like so. Okay, now, if you get to a certain electrical potential difference, okay, which is around negative 40 millivolts, okay, then you activate these voltage-gated sodium channels and these voltage-gated potassium channels. Okay, so of course one little channel here is not going to be great enough to produce a depolarization of the electrical potential difference across the cell membrane up to negative 40 millivolts. But if you have enough of them, then potentially it will be. Okay, and this electrical potential difference, this key electrical potential difference of around negative 40 millivolts is known as the threshold potential, okay? And if you go beyond that, you will activate the firing of an action potential, providing we have voltage-gated sodium channels and voltage-gated potassium channels open. Now, both voltage-gated sodium channels and voltage-gated potassium channels are activated at about the same threshold potential of around negative 40 millivolts. So we're going to activate both of these now to open, okay? But the voltage-gated sodium channels will open extremely rapidly, Whereas the voltage-gated potassium channels, they are much, much more slow about opening. So at the moment, all that's going to open is the voltage-gated sodium channels, and these are going to open much, much later. They're really, really slow about opening, but they have received the signal to open, basically. It's just they are very slow about doing it. Okay, so what happens is almost instantly the voltage-gated sodium channels will open, and they will now continue the work of this original sodium channel here, which was responding to the stimulus. Okay, but they will do it so much better than these channels. So sodium will come in through the voltage-gated sodium channels, and you will get a massive upstroke in the electrical potential difference across the cell membrane. Okay, so you're bringing in positive charge into the cell, you're raising the electrical potential intracellularly and lowering the electrical potential extracellularly, and therefore this number is just going to become more and more positive, and eventually it does actually become positive, and it goes up to around plus 40 millivolts up here. Okay, and then the voltage-gated sodium channels close. However, they do not close because you've got to plus 40 millivolts. They close just on a timing basis, as we'll see soon. Okay, so we will study their opening and closing properties very carefully. Okay, so these close on a timing basis. They're open for around 1 millisecond. So 1,000th of a second they're open for, and then after that they close. And by the time they've closed, they've got the electrical potential difference across the cell membrane up to around plus 40 millivolts. Now, just at the point that these voltage-gated sodium channels start to close after 1 millisecond, the voltage-gated potassium channels just about get round to opening. Okay, so this is key to understanding this. They were activated to open down here as well, not up here. It's a big misconception that it took an electrical potential difference across the cell membrane of plus 40 millivolts to activate these. No, they were activated at a similar level to the voltage-gated sodium channels. Okay, it's just that they took much longer to get around to actually opening. Now, the voltage-gated potassium channels are therefore going to open now. What are they going to do? Well, to understand which way the potassium ions are going to move, we need to consider the electrical potential difference across the cell membrane, and we also need to consider the concentration gradient for potassium across the cell membrane. So, extracellular potassium concentration is around 4 millimolar, okay? Intracellular potassium concentration is around 155 millimolar. So the concentration gradient for potassium is around 40-fold, favouring the movement of potassium out of the cell, basically. Okay? In addition, at the moment, the electrical potential difference across the cell membrane is at plus 40 millivolts, okay, which means that the intracellular electrical potential is actually greater than the extracellular electrical potential by 40 millivolts, okay. Potassium is a positively charged ion, just like sodium, so it now wants to be where the electrical potential is lower, which is the extracellular compartment. So at the moment, both the electrical gradient and the concentration gradient are telling the potassium ions to have a net movement out, basically. Okay, so what's going to happen is you're going to move positive charge out of the cell, and this is exactly the opposite to bringing positive charge into the cell. So when you move positive charge out of the cell, the electrical potential intracellularly is going to go down because you're losing positive charge from the intracellular compartment, whilst the electrical potential extracellularly is going to go up because we're dumping positive charge into the extracellular compartment. Okay, right. Now if we take this number up, okay, so this number's going up now, and we're taking this number down, okay, of course the number's going to become more negative again, because this number's getting smaller and the number we're subtracting off is going up, okay? So you're going to basically repolarize the electrical potential difference across the cell membrane. Okay, so you're now going to have the down phase of the action potential like so. Okay, now, we now need to discuss this. I need to update my argument a little bit because we've now gone back to a negative electrical potential difference across the cell membrane. And you might be wondering, well, you said that the potassium ions were moving out because of their concentration gradient and also because of this electrical gradient initially, because the intracellular electrical potential was greater than the extracellular electrical potential for this little bit up here. But now we're back to a negative electrical potential difference across the cell membrane, which means that the intracellular compartment now has the lower electrical potential of the two, so surely the potassium will start moving in the opposite direction. No is the answer, and the reason is that the concentration gradient is still stronger than the electrical gradient. You are correct in saying that as soon as we go to a negative electrical potential difference across the cell membrane, that the electrical gradient will favour the movement of potassium in, okay? But the concentration gradient is still there, okay? It's still 40-fold favouring the movement of potassium out, okay? And something very important to stress, actually, is that the number of sodium and potassium ions that actually move through these channels in an action potential is minuscule. Okay, absolutely minuscule compared to the number that are actually floating around in solution. You don't actually need that many ions to move through these channels to get a decent change in electrical potential difference across the cell membrane. However, the actual change to the concentrations is absolutely negligible. And you have to realize that, 1 mole is 10 to the 23 sodium ions. Okay, so we're talking massive amounts of sodium ions. The numbers which move through these channels to create these electrical maneuvers are tiny compared to that. So the action potential really is a measurable phenomenon with regards to the change in electrical potential difference, but not with regards to the actual movement of ions. Okay, yes, it is the movement of ions which causes the change in electrical potential, but really this is the macroscopic phenomenon, whilst this is minuscule, basically. Okay, so you get a noticeable change in the electrical potential difference, which is of huge importance, but you don't get important changes in the concentrations of the ions on either side. So you don't need to worry about, are the concentrations changing? No, basically, they will remain the same. Okay, at least to all decent approximations. Right, so the concentration gradient is still 40-fold, favouring the movement of potassium ions out of the cell. Okay, so that concentration gradient beats the electrical gradient, at least whilst the electrical gradient is depolarized of negative 85 millivolts. Now, what do I mean by that? Basically, if you want to stop the movement of potassium ions out of the cell through potassium channels, because of this concentration gradient, you need to take the electrical gradient across the cell membrane down to negative 85 millivolts. Okay, so for instance, I'm looking at a point at around negative 20 millivolts here. My assertion is that that is not strong enough to stop the movement of potassium ions out because of the concentration gradient. To stop the movements of potassium ions out because of the concentration gradient, you would need to take the electrical potential difference across the cell membrane down to negative 85. Okay? Whenever the electrical potential difference across the cell membrane is above that, for instance, negative 20, negative 40, negative 65, yes, the electrical gradient will be weakening and reducing the amount of potassium ions which move out, but it will not completely take it to zilch. Okay, and if you go below this, if you go down to negative 95, then the opposite will happen. The electrical gradient will now be stronger than the concentration gradient, and you'll actually get the movement of potassium ions in. So basically, although as soon as the electrical potential difference across the cell membrane becomes negative, the movement of potassium ions out will become smaller. Okay, so the number that are actually moving will decrease because the electrical gradient is now saying go the opposite way. It doesn't go to zero. It's always going to have a movement outward, at least whilst the electrical potential difference is above negative 85 millivolts. Okay, right. So potassium ions keep coming out and out and out and taking the electrical potential difference down and down and down, and you get to a level just hyperpolarized of negative 65. Okay, not quite down to negative 85, maybe down to negative 70 or somewhere around there. And then what happens is the voltage-gated potassium channels close, and they close for the same reason as the voltage-gated sodium channels. It's a timing thing. They only want to remain open for a certain amount of time, then they inactivate. Okay, so they inactivate too. Now both the voltage-gated sodium channels and the voltage-gated potassium channels have stopped conducting. Okay, they're both closed. And what will now happen is it returns back to resting membrane potential, because the only channels that are now open, we'll assume the stimulus has gone away now, the only channels that are now open are the leaky sodium and the leaky potassium channels, and they will restore equilibrium potential basically via the Goldman-Hodgkin-Katz constant field equation. Okay, right, so that's the action potential then. So that gives us the motivation for studying voltage-gated sodium channels, because what we now want to try and explain is firstly how the voltage-gated sodium channels open when the electrical potential difference across the cell membrane gets to negative 40 millivolts, okay, to threshold potential. And we also want to explain what happens after 1 millisecond that leads to these channels closing, even though the electrical potential difference across the cell membrane is still beyond this threshold potential. So those are our motivatory questions. How do you open the channels? How do you inactivate the channels? Okay, right. And another interesting thing that I haven't actually discussed here is that the voltage-gated sodium channels will remain inactivated until the electrical potential difference comes back down to around resting potential of around negative 65 millivolts. So to get them to reopen again, you have to firstly take the membrane electrical potential difference back down to resting membrane potential. And now, once you're back down here, then you can depolarize the electrical potential difference across the cell membrane again, and then activate them all over again. But you can't get them to activate without taking the electrical potential difference back down again beforehand. Okay, this stops you firing action potentials midway through another action potential, basically. It stops the voltage-gated sodium channels activating until, activating again until the action potential is actually finished. Okay, right, so we'll call it there for this video, and in the next video we'll begin our in-depth study of the voltage-gated sodium channels, beginning with their structure.